Welcome to the infinite expanse, a journey through the cosmos to understand the sheer vastness of the universe. Prepare to embark on a voyage that stretches the limits of our imagination and scientific understanding. From the smallest particles to the largest structures, we'll explore the incredible scale of everything that exists. Our journey begins over 13.8 billion years ago with the Big Bang. This monumental event marked the birth of the universe, a moment when all matter, energy, space, and time originated from a singularity, a point of infinite density and temperature. The universe began expanding at an unimaginable rate, and it continues to expand to this day. In the first few moments after the Big Bang, the universe underwent rapid inflation, expanding faster than the speed of light. This period of inflation smoothed out any irregularities, setting the stage for the formation of matter and the large-scale structure we observe today. As the universe cooled, protons and neutrons combined to form the first atomic nuclei in a process called nucleosynthesis. About 380,000 years later, electrons combined with these nuclei to form neutral atoms, primarily hydrogen and helium. This era, known as recombination, allowed light to travel freely through space, creating the cosmic microwave background radiation, a faint glow that still permeates the universe and provides a snapshot of its early conditions. Let's start with something closer to home, our solar system. The Sun, a medium-sized star, is at the center. It accounts for 99.86% of the total mass of the solar system. Orbiting the Sun are 8 planets, their moons, and countless smaller objects like asteroids and comets. To grasp the scale, consider this. Earth is about 93 million miles, or 150 million kilometers, from the Sun. Light, the fastest thing in the universe, takes about 8 minutes and 20 seconds to travel this distance. Neptune, the farthest planet from the Sun, is about 2.8 billion miles, or 4.5 billion kilometers, away. It takes light over 4 hours to travel from the Sun to Neptune. Our solar system extends far beyond the orbit of Neptune, into the Kuiper Belt and the Oort cloud. The Kuiper Belt, a region of icy bodies and dwarf planets like Pluto, stretches from about 30 to 55 astronomical units, or AUs, from the Sun. 1 AU is the average distance between Earth and the Sun, about 93 million miles. The Oort cloud, a hypothetical spherical shell of icy objects, is believed to surround the solar system at distances ranging from 2,000 to 100,000 AU. It's from here that long-period comets are thought to originate, occasionally visiting the inner solar system. Leaving our solar system, we enter the vast expanse of our Milky Way galaxy. The Milky Way is a barred spiral galaxy, about 100,000 light-years in diameter. It contains an estimated 100 to 400 billion stars and at least as many planets. Our solar system is located in the Orion Arm, about 27,000 light-years from the galactic center. The Milky Way is a complex and dynamic structure. Its spiral arms are regions of high star formation, filled with young, bright stars and stellar nurseries. At the center lies a supermassive black hole, Sagittarius A, with a mass of about 4 million times that of our Sun. Surrounding the galactic center is the bulge, a densely packed region of older stars. The galaxy is not a flat disk, but has a slight warp, likely caused by gravitational interactions with satellite galaxies like the Large and Small Magellanic Clouds. These satellite galaxies, along with the Milky Way, are part of a larger structure known as the Local Group. Beyond the Milky Way, we encounter our neighboring galaxies. The Andromeda Galaxy, the closest spiral galaxy to us, is about 2.537 million light-years away. It is on a collision course with the Milky Way, expected to merge in about 4.5 billion years. This future collision will create a new galaxy, sometimes referred to as Milkomeda or Milkdromeda. The Triangulum Galaxy, another prominent member of the Local Group, is about 3 million light-years away. It is the third largest galaxy in the Local Group and contains a rich array of star clusters and nebulae. Our Milky Way, Andromeda, and Triangulum are part of the local group, a collection of more than 50 galaxies. The local group spans about 10 million light-years and is gravitationally bound. It is part of an even larger structure called the Virgo supercluster. The Virgo supercluster is an enormous collection of galaxies, about 110 million light-years in diameter. It contains the Virgo cluster, the central and most massive cluster in the supercluster, with over 1,300 member galaxies. The local group resides on the outskirts of this supercluster. Superclusters are among the largest structures in the universe, consisting of thousands of galaxies bound together by gravity. However, they are not isolated, but form part of a vast network called the cosmic web. This web-like structure is made up of galaxy filaments, clusters, and voids, creating a complex and interconnected cosmic tapestry. As we delve deeper into the structure of the universe, we discover the cosmic web. Galaxies are not randomly distributed but form a vast, intricate web-like pattern. Filaments of galaxies stretch across millions of light-years, intersecting at nodes where galaxy clusters reside. Vast voids, nearly empty regions, exist between these filaments. This large-scale structure is a result of the gravitational pull of dark matter, an invisible substance that makes up about 27% of the universe's mass energy content. Dark matter acts as a scaffolding for galaxy formation, with ordinary matter gathering in regions of high dark matter density. The cosmic web's filaments are vast structures, sometimes stretching over 100 million light-years. They are composed of galaxies, gas, and dark matter, and their intersections form galaxy clusters and superclusters. These structures provide a framework for understanding the distribution and evolution of galaxies in the universe. One of the most astounding discoveries of modern astronomy is that the universe is expanding. Edwin Hubble, in 1929, observed that galaxies are moving away from us, and the farther they are, the faster they recede. This observation led to the formulation of Hubble's law and the realization that the universe itself is stretching. The expansion of the universe is driven by dark energy, a mysterious force that makes up about 68% of the universe's mass energy content. Unlike gravity, which pulls objects together, dark energy causes space to expand, pushing galaxies apart at an accelerating rate. This discovery has profound implications for the fate of the universe. If dark energy continues to drive the expansion, the universe will keep stretching, possibly leading to a big freeze where galaxies move so far apart that stars burn out, and the universe becomes a cold, dark, and desolate place. Alternatively, if dark energy changes over time, it could lead to different scenarios like the Big Rip or a Big Crunch. Now, let's zoom out even further to the observable universe. This is the portion of the universe we can see, limited by the speed of light and the age of the universe. The observable universe has a radius of about 46.5 billion light-years, making it about 93 billion light-years in diameter. It contains an estimated 2 trillion galaxies, each with hundreds of billions of stars and even more planets. The sheer number of stars in the observable universe is mind-boggling. Approximately 1 septillion, that's 1 followed by 24 zeros. These galaxies are spread across the cosmic web, forming clusters, superclusters, and vast voids. The observable universe is only a part of the entire universe, which might be much larger or even infinite. Our view is limited by the light that has had time to reach us since the Big Bang, about 13.8 billion years ago. Beyond this horizon lies the unobservable universe, regions we cannot see and may never be able to explore. Beyond the observable universe lies the realm of theoretical physics, where concepts like the multiverse come into play. The multiverse theory suggests that our universe might be one of countless others, each with its own laws of physics, constants, and conditions. Several theories support the multiverse idea. In the inflationary multiverse, different regions of space undergo rapid expansion at different rates, creating bubble universes with varying properties. In the string theory landscape, different solutions to string theory's equations correspond to different universes with diverse physical laws. While this idea remains speculative and unproven, it pushes the boundaries of our understanding and hints at an even greater expanse beyond our cosmic horizon. If true, the multiverse could provide answers to fundamental questions about the nature of reality and the origins of our universe. As we explore the universe, we encounter some of its most fascinating and mysterious objects. Black holes. These are regions of space where gravity is so strong that nothing, not even light, can escape. Black holes form when massive stars collapse under their own gravity at the end of their life cycles. There are different types of black holes. Stellar mass black holes, which are a few times the mass of the Sun. Intermediate mass black holes, with masses ranging from hundreds to thousands of solar masses, and supermassive black holes, which reside at the centers of galaxies and have masses ranging from millions to billions of times that of the Sun. Black holes are not empty voids, but have incredibly dense cores called singularities. Surrounding the singularity is the event horizon, the point beyond which nothing can escape the black hole's gravitational pull. Black holes can also interact with their surroundings, accreting matter and emitting powerful jets of energy. Other exotic objects in the universe include neutron stars, the remnants of massive stars that have undergone supernova explosions. Neutron stars are incredibly dense, with masses comparable to the Sun, but diameters of only about 20 kilometers. Their intense gravitational fields and rapid rotations can produce phenomena like pulsars and magnetars. Stars are the fundamental building blocks of the universe, and their life cycles play a crucial role in shaping the cosmos. Stars form in giant molecular clouds, regions of cold, dense gas and dust. Gravity causes these clouds to collapse, forming protostars that eventually ignite nuclear fusion in their cores. The life cycle of a star depends on its mass. Low-mass stars, like our Sun, spend billions of years fusing hydrogen into helium. When they exhaust their hydrogen fuel, they expand into red giants and eventually shed their outer layers, leaving behind a white dwarf. High-mass stars have much shorter lifespans. They burn through their nuclear fuel quickly and end their lives in spectacular supernova explosions, enriching the interstellar creation medium and seeding future generations of stars and planets. The remnants of supernovae can form neutron stars or black holes, depending on the mass of the progenitor star. These remnants continue to influence their surroundings, shaping the evolution of galaxies and contributing to the dynamic nature of the universe. In recent decades, the search for exoplanets, planets orbiting stars outside our solar system, has revolutionized our understanding of the universe. The discovery of thousands of exoplanets has revealed a staggering diversity of worlds, from hot Jupiters and super-Earths to potentially habitable Earth-like planets. Advanced telescopes like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, or TESS, have been instrumental in finding these distant worlds. They use techniques such as the transit method, where a planet passes in front of its star, causing a temporary dimming, and the radial velocity method, which detects wobbles in a star's motion caused by the gravitational pull of orbiting planets. The discovery of exoplanets in the habitable zone, the region around a star where conditions might be right for liquid water, has fueled the search for extraterrestrial life. While no definitive evidence of life beyond Earth has been found, the possibility of microbial life on moons like Europa and Enceladus, and the potential for life on exoplanets, continues to captivate scientists and the public alike. As we contemplate the vastness of the universe, it's essential to reflect on our place within it. Humans have always gazed at the stars, wondering about our origins and our destiny. From ancient astronomers to modern scientists, our quest to understand the cosmos has driven technological advancements and expanded our knowledge. Space exploration, through missions like the Hubble Space Telescope, Voyager probes, and future endeavors like the James Webb Space Telescope, continues to unveil the mysteries of the universe, bringing us closer to answering fundamental questions about existence. Human spaceflight, from the Apollo moon landings to the International Space Station, represents our first steps into the cosmos. Future missions to Mars and beyond aim to establish humanity as a multi-planetary species, ensuring our survival and opening new frontiers for exploration and discovery. Looking ahead, the future of the universe is a topic of great interest and speculation. Several scenarios are possible, depending on the properties of dark energy and the ultimate fate of the cosmic expansion. In the Big Freeze scenario, the universe continues to expand indefinitely, stars burn out, and galaxies drift apart. Eventually, the universe becomes a cold, dark, and lifeless place. In the Big Rip scenario, dark energy's influence increases, tearing apart galaxies, stars, and even atoms. Alternatively, the universe could experience a Big Crunch, where the expansion reverses, leading to a collapse back into a singularity. Another possibility is the Big Bounce, where the universe undergoes a series of expansions and contractions. Regardless of the ultimate fate, the study of the universe's future helps us understand the fundamental forces at work and our place in the grand cosmic scheme. The universe is a vast, awe-inspiring expanse that stretches our imagination and challenges our understanding. From the smallest particles to the largest cosmic structures, each discovery reveals the incredible complexity and beauty of the cosmos. As we continue to explore and learn, we are reminded of our connection to the universe and the profound impact of our quest for knowledge. Thank you for joining us on this journey through the infinite expanse. The adventure of discovery never ends, and the universe always has more to reveal.